Hello, I am Shweta from BSc Chemistry Honors Final Year. So the source is Pradeep's Inorganic Chemistry. Now we will study about metal ligand bonding in transition metal complexes. The first theory given was valence bond theory. Valence bond theory was developed by Linus Pauling. According to valence bond theory, the bonding in metal complexes arises when a filled ligand orbital containing a pair of electrons overlaps with a vacant 3 orbital on the metal ions to give a covalent compound. Thus, valent bonding theory assumes the bonding between the metal or metal ion and the ligand to be purely covalent. The hybrid orbitals that metal atom uses in accepting the pair of electrons from the ligand are those that point in the directions of the ligands. So, there are some postulates of the valence bond theory. The first postulate is central metal atom or ion in the coordination compound offers a number of vacant orbitals which is equal to coordination number of metal atom or ion for the formation of coordinate bonds with the ligands. Second is the approximate atomic orbitals x, p or d. The metal hybridize to give a new set of orbitals of equivalent energy called hybrid orbitals. The hybrid orbitals are directed towards the ligand depending upon the geometry of the coordination compounds. Third is the d orbitals involved in the hybridization may be either inner like n-1 d orbitals or outer like nd orbitals. Thus, hybridization in case of octahedral may involve d2sp3 or sp3d2. Fourth is the vacant hybrid orbitals of the metal or metal ion overlap with the filled occupied orbitals of the ligands and form a coordinate bond L and M bond. Let us now take some examples. Like first is coordination number compounds with coordination number 4. The first is the nickel cyanide. The oxidation state of nickel in the complex nickel cyanide is +2. We can represent the electronic configuration of nickel ion by losing 2 electrons from the outermost 4s orbital. Electronic configuration is like argon 18 3d8 4s2. Thus, the electronic configuration of nickel ion is this 18 argon 3d8. So, there are 8 electrons in the outer orbitals of the nickel ion. 8 electron present in this will occupy in such a way that these have the 3d orbitals occupied by 2 electrons while the remaining 3d orbitals are singly occupied. There are two ways in which the coordination complexes of nickel with coordination number 4 can be formed. If the complex involves sp3 hybridization, it will have tetrahedral structure. So if the hybridization is sp3, the structure will be tetrahedral, and if the hybridization is d2sp3 or sp3d2, then it will be octahedral. In case the complex ion acquires tetrahedral structure, the hybridization is sp3. It means that the two unpaired electrons are not affected. And as a result, the coordination compound with sp3 hybridization be paramagnetic. However, square planar structure which involves dsp2 hybridization requires one of the 3d orbitals vacant for the hybridization. This is possible only if two unpaired 3d electrons are paired. Pairing makes one of the 3d orbitals empty. During this exercise, no unpaired electrons are left and the complex should be diamagnetic. Second example is of nickel chloride. The oxidation number of nickel in this is +2. This is obtained by the loss of 2 electrons from the 4s orbital of nickel as shown. Experimentally, the complex has been found to be paramagnetic, corresponding to 2 unpaired electrons. It implies that the 3d orbitals are not disturbed and the complex involves sp3 hybridization. As a result, the structure of the complex is tetrahedral. Third example is copper ammonia. An inspection of the complex reveals that the oxidation state of copper in the complex is +2. The resulting electronic configuration of copper is argon 18 3d9. According to Hund's rule, the 9d orbitals electrons occupy the 5 3d orbitals and only one orbital is singly occupied. In order to accommodate 4 ammonia molecules around Cu2 positive या copper ion, the metal ion exhibit two possible geometrical arrangements for the complex. If the complex is tetrahedral, it will involve sp3 hybridization and the complex will be paramagnetic. On the other hand, if the complex happens to be square planar, it will involve dsp2 hybridization and the complex will be paramagnetic again. Now, a natural question arises in which the true structure of copper ammonia is true, tetrahedral or square planar. Though this valence bond theory, in terms of orbital hybridization, was successful in interpreting the geometrical shapes of most of the complexes, however, the theory has some limitations, like it fails to explain the color and spectra of the complexes. It fails to explain the differences between measured and calculated magnetic moments. Although the theory is successful in predicting the number of unpaired electron in the complex. It also fails to explain why magnetic moment values varies with temperature. The theory fails to explain or offer any concrete explanation about the stabilities of the complexes. It fails to explain why there are some complexes which are inert, labile complexes are those in which one of the following ligand can be easily displaced by another ligand. On the other hand, inert ligand are those in which displacement of ligand is. So now to correct the mistakes of the valence bond theory, there is another theory is crystal field theory. So valence bond theory helps us to understand the bonding in coordination compound. However, the theory suffers because it neither accounts for the color of the coordination compounds or it neither nor explain the complexes are high spin whereas other are low spin. Crystal field theory, on the other hand, explains successfully the colors of the complexes as well as their magnetic properties. This theory was developed by physicists named H. Barth and V. Bloch to account for the color and magnetic properties of hydrated salts of transition metals. Originally, this theory was applied to transition metal ions in ionic crystals. That is why the theory is called crystal field theory. Chemists began to apply the crystal field theory to transition metal complexes in 1950s, and since that time inorganic chemistry has become an excited field of research. Crystal field theory considers the central metal ion and surrounding ligand as point charges. Point charges are electrical charges that exist at a single point. It is important to note that the point change has neither an area nor a volume. According to this theory, if the it is the electrostatic attraction between the metal ion and the ligand, and the holds it holds that the ligand to be the metal ion. In brief, crystal field theory assumes the bond between the metal ion and the ligand as completely electrostatic. In case the ligand happens to be negatively charged ion such as cyanide, bromine and iodine ion, the interaction between the metal and the ligand is referred as ion-ion interaction. In case the ligand happens to be neutral molecule, like it can be ammonia, the nitrogen in NH3 requires a negative charge, a partially negative, and the hydrogen acquires a positive charge. In such cases, the interaction of the metal ion with the ligand is referred as ion dipole interaction. Now we will study some assumptions of the crystal field theory. It's also called CFT. Crystal field theory is now more widely used than the valence bond theory. It considers the attraction between central metal ion and the ligand as purely electrostatic. There are some postulates. The transition metal ion is surrounded by a number of ligands with lone pair of electrons. The ligands are treated as point charges. Point charges are electrical charges that exist as a single point. It is important to remark that the point charges have neither an area nor a volume. The ligand may be neutral or negatively charged species. In case the ligands are neutral, such as ammonia and water, it is the negative end of the dipole that is oriented towards the metal ion that accounts for the electrostatic interaction. In case of negatively charged, such as chlorine, C2O4, 2 negative, Cn negative, the interaction between central metal ion and the ligand is purely ionic. Next postulate is all the 5d orbitals of the isolated gaseous metal atom have the same energy. These 5d orbitals have of the gaseous atom possessing the same energies are called degenerate orbitals. Degenerate means the energies of all the orbitals is same. If a spherically symmetrical field of negative charge is placed around the metal ion, all the 5d orbitals of the metal ion will be raised in energy as a repulsion between negative field and negative charge electrons of the orbitals. In brief, the energy of the orbitals is raised because of the repulsion between the field and the electrons on the metal. However, the energy of the 5d orbitals will still remain degenerate. If the electric field results from the influence of real ligand, then the electric field is not spherically symmetrical because of the finite number 4 and 6 of ligand involved. In such a case, the d orbitals are not affected equally by the electric field of the ligands. We have also noted that the d orbitals have different orientations in space, and therefore these orbitals will experience different interaction from the ligand. So the CFT is defined as the splitting of energy of the 5 degenerate d orbitals of the metal ion into two different set of orbitals into different energies in the presence of electric field of the ligand is called crystal field splitting. The next postulate is the number of ligand in the surrounding metal affects the energies of 5d orbitals. It means that the crystal field splitting will be different with different coordination numbers. The properties of the coordination compound, such as magnetic properties and color, can be explained in terms of splitting of d orbitals in the different crystals. Now we will study about the factor affecting the crystal field parameters. So there are a number of factors which affect the extent of splitting of d orbitals by the ligands. These are: first, the nature of the ligands. The crystal field splitting depends primarily on the nature of the ligands surrounding the metal ion. The greater the ease with which the ligands can approach the metal ion, the greater will be the crystal field splitting. The ligands which cause smaller crystal field splitting are called weak field ligands, and the ligands which cause large crystal field splitting are called strong field. So, ligands can be arranged in a series that is called a spectrochemical series according to increasing magnitude of crystal field splitting as shown. So, the value or the strength of the ligand increases from iodine, bromine, chlorine, SCN negative, F negative, OH negative, OX2 negative, H2O, then ammonia, then ethyl diamine, then NO2 negative, Cn negative, CO. So the in this way the the strength of the ligand increases. So second factor affecting is oxidation state of metal ion. The magnitude of the crystal field splitting depends upon the oxidation state of the central metal ion. Trivalent metal ions causes larger crystal field splitting than the divalent metal ions. For example, the crystal field splitting in trivalent cobalt complex COH2O6 3 positive, then the divalent metal ion is 18,600, whereas the corresponding divalent COH2O6 2 positive, the CFSE is only like 9,400. So the increase in the crystal field splitting is due to increased charge on the metal ion that tends to pull the negatively charged ligand more effectively towards itself. The third factor is type of d orbitals. The magnitude of the crystal field splitting within the same transition series as shown do not vary greatly. However, appreciable changes in the crystal field splitting occur in moving from 3D to 4D, and almost similar increase in the crystal field splitting is observed on moving from 4D to 5D transition series. Fourth factor affecting the nature or the strength of the complexes is geometry of the complex. The crystal field splitting energy in case of tetrahedral is less than that of an octahedral complex. This is because there are only 4 ligands in the tetrahedral as compared to 6 ligands in case of octahedral field. In addition, there is a ligand along each axis on the octahedral field, whereas no ligand lies directly along any axis in tetrahedral field. The splitting of the tetrahedral complex is defined as nearly half of the splitting in the octahedral complexes. So there is a relation between these both. So the splitting in tetrahedral complexes is 4 by 9 of the splitting in the octahedral complexes.